All right, chemistry. Let's finish up our chapter 5 video lectures. So this is your second part of your chapter 5 video lecture. After this video, I want you to be able to define the atomic and ionic radii, ionization energy, and electron affinity, as well as electronegativity. Right? So these are going to be different types of trends that you can observe on the periodic table. But in order to know what they are, you have to be able to define them. I want you to be able to compare the periodic trends of atomic radii, ionization energy, and electronegativity, and then state the reasons for these variations. Define valence electrons and state how many are present in atoms of each main group element, and compare the atomic radii, ionization energies, and electronegativities of the d block elements with those of the main block elements. So here we go. Now to get a little bit more specific, we need to be able to describe those periodic trends, right? Ionization energy, and relate them to atomic structures. Periodic trend in atomic, sorry, that's not radium, radius, and relate them to atomic structures. Describe the periodic trend in electronegativity, and relate them to atomic structures. And then describe that periodic trend in ionic size, electron affinity, and then melting and boiling points, right? Again, relating them to the atomic structures. So we have these periodic trends. Not only do we want to know what the periodic trends are, be able to say what the periodic trend does on the periodic table, but also relate each of them to the atomic structure. So the arrangement of the periodic table reveals trends in the properties of elements. You should already know this because as you go down a group, you see that each element in that group has the same number of valence electrons, and because the valence electrons determine the chemical characteristics, all the elements within a group have similar chemical characteristics. A trend is a predictable change in a particular direction. Now, when we say that you have to know what the ionization energy is, or the trend for ionization energy across a period or down a group, we're not saying that you have to remember the value, what the absolute value for the ionization energy is. You just need to know how it changes. Does it increase or decrease as you go across a period or as you go down a group? Understanding a trend among the elements enables you to make predictions about the chemical behavior of the elements. These trends in properties of the elements in a group or period can be explained in terms of electron configurations. Again, looking at the electrons that are available for bonding. The first we're going to start with is ionization energy. The ionization energy is the energy required to remove an electron from an atom or ion. And so we have A representing the neutral atom plus energy, right, the ionization energy. We will form not a neutral atom anymore. We'll have an ion, and we will eject an electron. The electron is gone. So here's an example. We have lithium, a neutral lithium atom, right? We add energy. It has to be sufficient energy. It has to be enough to actually eject that electron. It's called ionization energy. But once we add that amount of energy, this lithium will lose an electron because that electron will be ejected, right, emitted, and we'll have a lithium ion, right, like a lithium ion battery. We'll have a lithium ion plus that electron that has been ejected, right? So here's my lithium ion, and here's my ejected electron. So ionization energy. Ionization energy decreases as you move down a group. So as you go down a group on the periodic table, ionization energy is decreasing, meaning it's easier to ionize as you go down a group. Each element has more occupied energy levels than the one above it has. So the outermost electrons are farthest from the nucleus and the elements near the bottom of a group, right? Because as you go down the group, those outermost electrons are getting further and further from the nucleus. So as you move down a group, each successive element contains more electrons in the energy levels between the nucleus and the outermost electrons, which results in something called electron shielding. Electron shielding is the reduction of the attractive force between the positively charged nucleus and its outermost electrons due to the cancellation of some of the positive charge by the negative charges of the inner electrons. Because remember, picture what's going on with this with this atom, this really, really large atom with lots and lots of electrons. You have a very positively charged nucleus. You have a valence electrons very far away from the nucleus, and then you have, potentially dozens of inner shell electrons in between that valence electron and the nucleus. So while truly there's an attraction between the nucleus and the valence electron, but there's also a repulsion, right? A negative electron-electron repulsion between the inner electrons and that valence electrons, and it kind of cancels out some of the attraction to the nucleus. So because the attraction to the nucleus goes down, right? That means that those valence electrons aren't being held nearly as tightly. Therefore, it's easier to eject them. Hence, ionization energy decreases. So here's a graphic representation of the ionization energy trend, right? Decreases as you go down a group, and it will increase as you go to the right within a period. So ionization energy tends to increase as you move from left to right across a period, like we just saw. From one element to the next within a period, the number of protons and the number of electrons increase by 1, right? Each element you go over, you're increasing by 1. The additional proton increases the nuclear charge, right? Because the proton is positively charged, so when you add a proton, you get more positive charge overall. This higher nuclear charge more strongly attracts those outer electrons, as long as they're in the same energy level, right? In the same row, in the same period. But the electron shielding effect from the inner level electrons remains the same, right? So the shielding is the same because the number of inner shell electrons are the same, but we're increasing the amount of positive charge in the nucleus, and so we're actually holding those outer electrons more tightly. And since we're holding them more tightly, it takes more energy to eject an electron. So ionization energy tends to increase. So here's another graphical representation of ionization energies as you're moving across a period. And you see as you go from the group 1 elements all the way over to the group 18 elements, you're seeing a general increase in ionization energy. Now, there are some dips there as you go along, but in general, there is an overall increase. All right, so that title says ionization, but we're actually going to start talking about atomic radius of the main block elements. So this graphic, so ignore this, that's a little bit of a typo. Read this, atomic radii of main block elements. So starting with group 1, as you go to the right on the periodic table, as you go to all the way over to group 18, you'll see that the atomic radius, which is to say the size of the atom, is getting smaller. Smaller. As you move from left to right in the periodic table, the radius of an atom tends to get smaller. Now, the exact size of an atom is very, very hard to determine because, remember, the volume of the electrons, right? The volume that the electrons occupy is thought of as a cloud, right? The electron cloud. And because it's a cloud, it has no clear-cut edge. In addition, the physical and chemical state of an atom can change the size of that electron cloud. And so determining atomic radius is a little bit tricky. One method for calculating the size of an atom involves calculating the bond radius, which is half the distance from center to center of two like atoms bonded together. So the bond radius can change slightly depending on what atoms are involved. So if I have I2, I have two atoms bonded together, and instead of trying to measure the edge of this cloud, which is very, very tricky, or essentially impossible, what I do is I measure the distance between the center of this nucleus and the center of this nucleus, and that's the bond length, right? That's the bond length. So this would be essentially the diameter of the atom. Sorry, I got my tongue a little tied there. So we see that this is the electron cloud, and so it'll be 2 radii, right, for the diameter of the atom. If I go from nucleus to nucleus, I have 2 radii, right? So that's why the atomic radius is half the bond length, right? Half the bond length. Again, the bond length is determined by the distance between the two nuclei that are bonded together, and bond length helps you determine atomic radius. Atomic radius is half the bond length, right? Just this distance, half the bond length. So atomic radius increases as you move down a group, as you go down a group. So atomic radius decreases as you move to the right within a period, but it increases as you move down a group. Because as you proceed from one element down to the next within a group, another principal energy level has been filled. The addition of another level of electrons increases the size, which here we call it atomic radius, of an atom. Because of electron shielding, the effective nuclear charge acting on the outer electrons is almost constant as you move down a group, regardless of the energy level in which the outer electrons are located. But atomic, like we said, with the graphic at the beginning of this portion, atomic radius decreases as you move across a period. As you move from left to right across a period, each atom has one more proton and one more electron than the atom before it has. All additional electrons go into the same principal energy level, so no electrons are being added to the inner levels, meaning the electron shielding does not play a role as you move across the period because you're not increasing the electron shielding. But the nuclear charge increases as you go across a period, and so the effective nuclear charge acting on the outer electrons also increases. And so if that effective nuclear charge is increasing, you are increasing the hold. You're actually pulling them in closer to the nucleus, making the atomic radius smaller. So here's our graphic representing the trend in atomic radius that you are responsible for knowing. As you go down a group, atomic radius increases. As you go to the right within a group, in a period, the atomic radius decreases. So here's the graphic that you've already seen. But this is going to be the one that you're going to be asked lots and lots of questions about, this general trend. Now we're going to move on to ions, right? So we're going to talk about ionic radii. And so similar to atomic radius, as you move down a group, you'll see that the radius of an ion increases. But the radius of the ion will decrease as you move to the right within a period. So we have chlorine, right? So chlorine nucleus on one molecule, chlorine nucleus on an adjacent molecule. Okay, this is the distance between adjacent nuclei. The van der Waals radius, which is 170, okay, it's half of this distance, And so remember, we're using this type of measurement to figure out what the actual radius is. Now let's talk about electronegativity. One of the most important trends that you can memorize and use to figure out future things, electronegativity. Not all atoms in a compound share electrons equally. Okay, and we'll talk a lot more about that next chapter when we talk about bonding. Knowing how strongly each atom attracts bonding electrons can help explain the physical and chemical properties of that compound. Linus Pauling, an American chemist, made a scale of numerical values that reflect how much an atom in a molecule attracts electrons, which is called electronegativity values. Electronegativity is the measure of the ability of an atom in a chemical compound to attract electrons. How is that atom going to attract electrons? How strongly, how weakly? The atom with a higher electronegativity will pull on the electrons more strongly than the other atom will. Fluorine is the element whose atoms most strongly attract shared electrons within a compound. Pauling arbitrarily gave fluorine an electronegativity value of 4.0. Values of the other elements were calculated in relation to this arbitrary point. Electronegativity values generally decrease as you move down a group, because the more protons an atom has, the more strongly it should attract an electron. However, electron shielding is playing a role here again. Electronegativity usually increases as you move from left to right within a period, because as you proceed across a period, each atom has one more proton and one more electron in the same principal energy level than the atom before it has. This means that electron shielding does not change as you move across a period because no electrons are being added to inner levels. The effective nuclear charge increases across a period because of the increase in number of protons that's not being mitigated by an increase in electron shielding. So as this increases, electrons are attracted much more strongly, resulting in an increase in electronegativity. The increase in electronegativity across a period is much more dramatic than the decrease in electronegativity down a group. And so here's our trend for electronegativity that you're responsible for remembering. As you go down a group, it decreases. As you go to the right across a period, it increases. So here are some more exact values, and you'll see this trend in action. Again, every single change between atoms isn't always an increase, right? So you see here we're having actually small drops. But in general, there is a trend. There's a trend to have electronegativity increase as you move to the right across a period. The effective nuclear charge and electron shielding are often used in explaining the reasons for periodic trends. And so as you've listened to this video, you've heard me mention effective nuclear charge, referring to the number of protons and electrons. You've also heard me refer to electron shielding. These are the types of things that you need to use to explain your trends when you are asked about them. So effective nuclear charge and electron shielding also account for two other periodic trends, ionic size and electron affinity. The trends in melting and boiling point are determined by how electrons form pairs as the d orbitals fill. So, getting on to ionic size and electron affinity. Like atomic size, ionic size has periodic trends. As you proceed down a group, the outermost electron in ions are in higher energy levels. The ionic radius usually increases as you move down a group. This trend holds for both positive and negative ions. Metals tend to lose one or more electrons and form a positive ion. Now, as you move across a period, the ionic radii of metal cations tend to decrease because of the increasing nuclear charge. Why do we have an increasing nuclear charge? Because we're adding a proton each time we move to the right, but we're also losing electrons, and so the effective nuclear charge, because we're ionizing, right? That's why we're an ion, because we lost electrons. That effective nuclear charge is going way up. The atoms of nonmetal elements in a period tend to gain electrons to form negative cations. So as you proceed through the anions on the right side of the period, ionic radii still tend to decrease because of the anions increasing nuclear charge, right? We have more positive in the nucleus and we have more negative in the cloud, and so that electrostatic attraction is increasing. So again, here's our representation of the ionic radii trend. Now we're on to electron affinity, and this is one of the most difficult trends for students to wrap their head around, because we start talking about amounts of energy, and we use negative values here. And I want to try to make this very clear. A negative value is not the same as a negative number. It does not mean it's less energy than zero. Okay. In thermodynamics, which we're not going to really do a lot here, thermodynamics in Gen Chem, a negative value simply indicates that that much energy is leaving the system. A positive energy value indicates that that much energy is entering the system, right? So the positive or negative sign isn't really saying positive or negative value. It's indicating the direction that that amount of energy is moving. So if you can start your understanding of electron affinity with that in mind, this will be a lot easier for you. So the energy change, right, because it's either leaving or being gained, the energy change that occurs when a neutral atom gains an electron, when it gains an electron, is called the atom's electron affinity. This property of an atom is different from electronegativity, right? Not the tendency to attract another electron. This is the energy change when an atom actually does gain an electron. It's the energy change. The electron affinity tends to decrease as you move down a group because of the increasing effect of electron shielding. Electron affinity tends to increase as you move across a period because of the increasing nuclear charge. So here's your trend that you're responsible for remembering. For electron affinity, you decrease as you go down a group, but you increase as you move across a period.
Some elements acquire electrons to form negative ions. In the case of chlorine, the formation of a negative ion is favored because the resulting chlorine has a full octet. In general, the closer the atom is to acquiring a full octet, the more strongly it attracts electrons. Chlorine has 7 valence electrons, and its electron affinity is negative 361.7. By convention, the more negative the number, the more strongly the atom attracts the negative electrons. Phosphorus has 5 valence electrons and an electron affinity of only negative 74.6. The electron affinity of aluminum, with 3 valence electrons, is negative 44.1. Because of the way electrons form orbitals, there are some lapses in this pattern. Nevertheless, the general trend holds.
So let's move on to talk about melting and boiling points. Instead of a generally increasing or decreasing trend, melting and boiling points reach 2 different peaks as the d and p orbitals fill, right? 2 different peaks, focusing on the d and p orbitals. From left to right across period 6, right? N is equal to 6, period 6, the melting and boiling points at first increase. Because as the number of electrons in each element increases, stronger bonds between atoms can form, right? When you have strong bonds, it takes more energy to melt or boil that particular element or that particular substance. As a result, more energy is needed for melting or boiling to occur. But near the middle of the D block, the melting and boiling points reach a peak. As more and more electrons are added, they begin to form pairs within the d orbitals. Remember our rules for filling orbitals back in chapter 4, right? As we go and doubly fill each orbital, right, we have more and more electrons, right? They're forming pairs inside of those d orbitals. Because of the decrease in unpaired electrons, right, because we're pairing more and more electrons, the bonds that the atoms form or can form with each other actually become weaker. As a result, these elements have lower melting and boiling points. For example, in period 6, cesium has a low melting and boiling point because it only has 1 valence electron to use for bonding. As you proceed past mercury, right, Hg, the melting and boiling point again begin to rise as electrons are now added to the p orbital. They continue to rise until they peak at the elements whose p orbitals are almost half filled. Another decrease is seen as electrons pair up to completely fill those p orbitals. The noble gases have no bonding forces between atoms, and so their melting and boiling points are usually very, very low. So here's a representation of that double peak system. So as we get to the middle of the D block, we have a peak, and then it'll start to decrease as you get to the end of the D block. As we enter the P block, we'll have another peak, and then we'll have another decrease as we get to the, for example, radon, a noble gas. And we start here, just looking at the melting point. Again, you see this double peak system. As you get to the middle of the D block, you get your peak. Then you head to the end of the D block, you get this trough right here, and then as you move into the P block, you get a small peak and then a decrease. So looking at this, this is a triple phase diagram, and so we see that as we have temperature, or which is energy, added to a system, right? If it's in the solid phase, right, we can increase the temperature of that substance. For example, water, if it's below 0 degrees Celsius, the temperature will increase until we get to 0 degrees Celsius. Now, we will stay at 0 degrees Celsius, so even though we're continuing to add energy to the system, the temperature will stay at 0 degrees Celsius until every single molecule of water has transitioned from the solid state into the liquid state, which is represented here in this middle portion. Now, once every single molecule has been changed to the liquid state, now as you continue to add energy, you now see that the temperature is starting to increase again until you get to 100 degrees Celsius, in which individual molecules start to transition from the liquid state into the gaseous state. But Remember, not until every single molecule of water has transitioned to that next state, not until every single molecule has done that, can the temperature increase. And so you continue to add energy to the system. You will not see an increase in temperature until it's all gas. Now, off the screen here, you would see once every single molecule is turned to gas, you would see an increase in overall temperature. So this is why if you boil a pot of water, when it's boiling, it is in the process of transitioning from liquid to the gas. Boiling water is at 100 degrees Celsius no matter how long you heat it. It's not until every single molecule of water has become gas that you can actually see an increase in temperature above 100 degrees Celsius.
The boiling point of water can be found on a phase diagram by starting at 1 atmosphere on the pressure axis and moving to the right until you reach the liquid vapor line. The temperature is read by tracing from the boiling point down to the temperature axis. This temperature is the normal boiling point of water.
So let's go through a quick recap of these periodic trends that you are responsible for. We have ionization energy decreases as you go down a group and increases as you go across a period. We have electronegativity decreases as you go down a group and increases as you go across a period. We have electron affinity that decreases as you go down a group and increases as you go across a period. All right, guys. I know this seems to be a lot at once, but once you get the general ideas of electron shielding and effective nuclear charge, these trends will start to be very, very intuitive for you, and you will do just fine. All right, guys. I will see you next period.